In this video, we're going to talk about coefficients of friction. Let's start by talking about the difference between static and kinetic friction. Here we have a graph of friction versus applied force, and in the first part of the graph, you'll notice that the friction and the applied force are equal. Now, this occurs when the object is stuck to a surface, and we call this the static friction region. Eventually, you'll push so hard that you reach this point right here, which we call the maximum static friction, or Fmax. And as soon as you push with that peak amount of force, the object will begin to move, and then the force of friction will stop varying from 0 to a maximum value and will decrease slightly to a constant value that we call the kinetic friction. So this region represents the kinetic force of friction. So remember that for static friction, the force of static friction, Fs, is going to be less than or equal to that maximum value. And for kinetic friction, Fk, it is constant. So it is just some value. So we're going to come back to this note in just a second and try and come up with an equation for us to be able to put a number to maximum static friction or kinetic friction. Let's take a look at a graph of maximum static friction versus normal force. So here we have a graph of maximum static friction versus normal force for a friction sled with a felt bottom on a lab tabletop. Now, you'll notice that there is a linear relationship between the maximum static friction and the normal force. So the slope here is going to represent for us the slope of a linear relationship. So I'd have the equation y equals mx plus b, but instead of y, we've got maximum static friction, Fmax, and instead of x, we have normal force, which we would write as n. And there would be, in this case, the y-intercept is very, very small, and we can pretend that it's basically 0. And the slope we call the coefficient of friction. So we would call this mu s for the coefficient of static friction. Now remember that friction and normal force are vectors. So I could write arrows above them, but the thing about coefficients of friction and friction forces, if you draw like a free body diagram, then you'd have maybe normal force up, weight force down, and then say friction to the left. Normal force and friction, they actually are, because they are 90 degrees apart, they really have no relationship to each other as directional vectors. And instead, we can only think about how their quantities are related to each other. So what's normal for us to do is to think about the absolute value or the magnitude of the vectors. So the long and formal way of writing that is by putting the absolute value bars around it. But you can also just not put an arrow above each letter, and we just sort of accept that what we're talking about is the number parts, and they're always going to be 90 degrees to each other, so we don't have to worry about angles. Great, so the slope of this line is the coefficient of friction, and it is a measure that lets us predict how much friction there will be between two surfaces if we know what the normal force between them is. Now, just a quick note on this. Remember that mu is a Greek letter. It's pronounced mu, kind of like the Pokemon. And it is the coefficient of friction. So sometimes it helps to actually write that down for yourself. Because you can forget that in a problem it'll say the coefficient is a number, and you're like, oh my God, what is that? Well, it's mu. That's what you write it equal to. Now, the other thing to note about this coefficient of friction, and really all coefficients of friction, is that the coefficient of static friction must be found experimentally. Must be found by experiment. There's no way to theoretically decide what the coefficient of friction between two surfaces is going to be. You have to just set up a lab and find out what it is. So now if we return to our static friction little note, we can remember that static friction doesn't have to be equal to the maximum value. It varies from 0, right, to some maximum value. So it's important for us to note that when we talk about coefficient of static friction, the coefficient of static friction relates to the maximum. And so we can say that the static friction is always less than or equal to the coefficient of static friction, which tells us about the max, times the normal force. So sometimes you'll see the equation for static friction written like this. It can be anything from 0 to the maximum. And the way that you can decide what the maximum is by using the static coefficient of friction and multiplying it by the normal force. So now let's take a look at the coefficient of kinetic friction. Here we have data from the same sled with a felt surface on a lab tabletop being moved, but now instead of pulling on the object until it begins to move, it constantly moves. And so we have a measure of kinetic friction versus normal force. Similarly, this is a linear relationship, y equals mx plus b, where we would say that y is Fk for the kinetic force of friction. The intercept is so small that it's basically 0. And for normal force, that's what we would do for x. And the slope of 0.21, we would call that the coefficient of kinetic friction, and we would use the Greek letter mu with a k to represent that we have found the coefficient of kinetic friction. Now, the coefficient of kinetic friction also must be found by experiment. There is no way to theoretically propose what mu k is. You just have to slide tires across the ground and figure out what is this value by getting a graph of friction and normal force. Now, the other interesting thing to note about the coefficient of kinetic friction is that it is always slightly less. Mu k is always slightly less than the coefficient of static friction, which tells us about the maximum static friction. So like here, I have 0.21 for the kinetic coefficient of friction. If we go back and look at the static friction for this exact same object, you'll notice that it is slightly bigger, 0.22. Sometimes the difference is so small that the coefficient is basically the same number, but you will always see that the kinetic coefficient of friction is slightly less, as long as there are no major sources of error in the experiment that you're using to find the coefficient of friction. So let's go back to our static versus kinetic friction note, and let's write the equation for kinetic friction. Fk is constant, and Fk is always equal to the coefficient of kinetic friction times the normal force. Okay, so this means that if you know what mu k is, you can find the kinetic friction. And for static friction, if you know what mu s is, then you don't necessarily know what the force of static friction is, but you know what the maximum value will be. And so sometimes you have to judge, like, is an object going to begin to slide? Because if you know what mu s is, then you can find the maximum static friction, and maybe there's a situation where there's more force than that static friction, and you know the object would begin to move. Okay, so now let's take a look at a simple example of the static and kinetic coefficients of friction and how we use them in problems. You push a 10-kilogram box at rest with increasing force until it finally moves when you push with 24 newtons of force. After the box has started to move, you only need to push with a force of 22 newtons to maintain the same speed. Okay, we are going to find the coefficient of static friction and then the coefficient of kinetic friction. Let's start with the coefficient of static friction. This problem is giving me information about the maximum static friction, Fmax. When it finally moves and you push with 24 newtons of force, that is Fmax, the maximum static friction. Now, you know that the mass of the box, 10 kilograms, can be used to find the normal force because we just use the weight of the object. Like if I draw a free body diagram, here's your push, 24 newtons. Fmax is equal to 24 newtons at that moment before it begins to move. And then there's the weight down. and the normal force up. And as long as this isn't on an elevator or something, then the normal force is equal to the weight. Okay, so mass times the acceleration due to gravity. We'll use 10 to simplify this. It's just 10 times 10, so 100 newtons. And now I have enough information to solve for the coefficient of friction. Remember that maximum friction, static friction, is equal to mu s, the coefficient of static friction, times the normal force. So if I want to find the coefficient of static friction, then I just divide my friction force by the normal force. So to find mu s, I take that 24 newtons and divide by 100, which gives me 0.24. Now notice that newtons cancel out, and I'm left with a number that is unitless. That is correct for the coefficient of friction, because the coefficient of friction is just a number that tells you the ratio of friction to normal force. So it's unitless or munitless. Okay, so let's write that mu s equals 0.24 up here for A. And now let's think about B. What is the coefficient of kinetic friction? Well, after the box has started to move, you only need to push with a force of 22 newtons to maintain the speed. So that means that if I draw a free body diagram, your force of 22 newtons is all you need. And again, you'd have weight, normal force. Those two are equal again. But you push with a force of 22 newtons to maintain the speed, and that means that your kinetic friction is also 22 newtons. The idea here is that this phrase, maintain the speed, means you're moving with a constant velocity, so no acceleration, not speeding up or slowing down, and the forces have to balance each other for that to be true. So that last sentence is telling you what the kinetic force of friction is. It's telling you the kinetic force of friction is 22 newtons. Okay, how do I find the normal force? Well, it's the same box with the same mass, so it's still 10 kilograms times 10 meters per second squared, or 100 newtons. And now finding the coefficient of kinetic friction comes from our equation, mu k times the normal force. And same as before, I'm just going to divide both sides by the normal force. And now I know that to find the coefficient of kinetic friction, I take that 22 newtons and I divide it by 100 newtons and get 0.22 for the coefficient of kinetic friction, which you'll notice is slightly smaller than the coefficient of static friction for that maximum static force. A 5 kilogram box is at rest on the floor and you start to push on it. The graph below shows the force of friction between the box and the floor as you apply more and more force. A. What is the coefficient of static friction between the box and the floor? B. What is the coefficient of, kinetic friction between the box and the floor? Okay, so we want to find mu s and mu k. Now, let's just kind of use our equations from before. We know that for static friction, we need the maximum. And so to find mu s, we take the maximum force of friction, F's max, and divide it by the normal force. And for kinetic friction, we need the kinetic coefficient. And to find it, we divide the kinetic force of friction by the normal force. Okay, so let's just leave these equations for mu here for ourselves so that we can think about what do we need to find. Okay, so the first thing that I'm going to need is the normal force. And if it's a 5 kilogram box and it's not on an elevator accelerating up or down, then I can just quickly calculate the normal force using mass and the acceleration due to gravity. So 5 kilograms times 10 meters per second squared gives me 50 newtons. So for both problems, I know the normal force is 50 newtons. Okay, so what do I do to find the maximum static friction, and what do I do to find the kinetic friction? Well, I take a look at the graph, and I recognize that from 0 to 40 newtons of friction, we're in the static region. And 40 appears to be the maximum static friction, so F's max. Okay, great. So 40 is what I use to find the coefficient of static friction. And 40 newtons divided by 50 newtons is going to give me 4/5 or 0.8. And again, remember, the coefficient is unitless because the newtons cancel each other out. Okay, what about the force of kinetic friction? Well, I look at the graph, and this region right here is where I have kinetic friction. So it looks like this value is about 35. And so I would use 35 as the force of kinetic friction. And 35 over 50 is going to give me 0.7. And again, the newtons cancel out, and it's unitless. Also, you'll notice that the coefficient of static friction is slightly more than the coefficient of kinetic friction. Let's do one more. A pickup truck is at rest at a stoplight. The light turns green and the truck begins to accelerate. A 20-kilogram toolbox is in the bed of the truck. The coefficient of kinetic friction between the truck and the bed is 0.3, while the coefficient of static friction is 0.4. What is the maximum acceleration that the truck can have before the toolbox begins to slide? So this is a very interesting and important question. Let's start by writing down what is 0.3 and what is 0.4. We're told that the static coefficient of friction is 0.4, so that's mu s. Remember, coefficient of friction is mu. Okay, then 0.3 is the coefficient of kinetic friction, so mu k is 0.3. And this problem wants us to find the maximum acceleration that the truck can have before the toolbox begins to slide. So I'm just going to go ahead and write A equals question mark. Now, if it's giving me coefficients of friction, then this problem is obviously about force. And if it asks me to find acceleration, then that means that I'm probably going to need to use our ultimate force equation that relates force to acceleration, which is, of course, the net force, sigma F, equals mass times acceleration. Or rearranged, acceleration is net force over mass. Now, anytime I'm going to look for net force, that is a hint or a clue that I should probably draw a free body diagram and figure out what is that net force. Is it a single force? Is it two forces being subtracted or added? So let's draw a little picture. Okay, here's your truck. It's amazing. You're so excited. You're driving the truck. You're like, yeah, and you're speeding up from the stoplight, and it's an awesome day, and you're so happy. Okay, cool. Well, there's a toolbox on the back of your truck. So I'm going to draw this toolbox just like absurdly big. And we'll assume that this is like a flatbed so that you can see where the surface of the toolbox is on the surface of the pickup truck. If you are moving forward and accelerating forward, then there's some, force that you are putting on the ground to make yourself go forward. But the toolbox is not connected to the ground. So the only thing that can cause this toolbox to accelerate with you to the right is a force of friction. That is acting in the same direction as the acceleration. Now, to finish the forces, you'd have a weight force down and a normal force up, which I can write it like that if I want. And I'm going to assume that the normal force and the weight are equal to each other. Okay, so now let's talk about this force of friction. What is it? Well, it's static if the toolbox is stuck to the truck bed. So the toolbox can move with the truck, but that won't be kinetic friction because it's still stuck to the truck bed, and we would call that static friction. But at some point, the friction between the toolbox and the truck bed would reach a kinetic place where they're sliding past each other. So this would be the point where the toolbox is no longer stuck to the truck bed and accelerating with it, but instead it's beginning to kind of slide towards the back because there's a kinetic force of friction pulling it along with the truck, but now they're unstuck and it's just going to sort of slide backwards in the truck bed until it hits the tailgate or falls off. So that's what this last sentence is asking us to focus on. What is the maximum maximum acceleration that the truck can have before the toolbox begins to slide? That's asking us to find F max, or to consider Fs max, because that is the last amount of friction, the highest amount of friction that can exist before the toolbox is no longer stuck to the truck bed and is free to slide around. Okay, so that means that in this scenario, we are looking at the net force as being the maximum force of static friction. So when I want to find the acceleration, I'm going to take F's max and divide it by the mass, which is great. Now, let's think about what the force of static friction, maximum static friction, is going to be. It's F's max, so I know that it's equal to mu s, the static coefficient of friction, times the normal force. Now, in this problem, though, I know that the normal force is equal to mg, the weight. So really, the maximum static friction is equal to mu s times mg. Okay, great. So what do I do with this? Well, to find the acceleration of this toolbox, I'm going to take this equation and plug it in for F's max. So I get acceleration equals mu s times the weight, mg, all over m. Now, I've gone ahead and not plugged in the numbers because I want to show you something that's really important, and it comes up pretty often. What if you didn't know what the mass of the toolbox was? What if it was just the toolbox? Well, it doesn't matter because m cancels out. And so now I found that the acceleration, the maximum acceleration, is equal to mu s times g, the acceleration due to gravity, or 0.4 times, we'll use 10 meters per second squared. So the maximum acceleration that the toolbox can have is 4 meters per second squared. Okay, great. So that's kind of a tricky problem, but that happens a lot in physics, where we want to write things in terms of m and g when we can, because we want to get rid of the mass. Because now I know it doesn't matter what the mass of the toolbox is. It could be 300 kilograms, it could be 2 kilograms. That's what the maximum acceleration of either of those things is going to be, so long as the coefficient of static friction is the same. Okay, this video was a little bit complicated, but hopefully you got something from it, and it's over.